Next speaker is Mr. Ollie Smeenk from SODAQ, and his talk will be about sustainable transportation solutions, exploring the benefits of smart labels and low-power technologies.
Thank you very much. Hi everyone, still awake? So I'm not going to teach you guys anything about printed electronics in the form of creating the printed electronics from a materials point of view or maybe from a production point of view, because most of you already know this much better than I do. Now, where I'm going to talk about is actually how do we use these printed electronics in the real world to make the world a more sustainable place. So I'm Ollie Smeenk. I'm co-founder of SODAQ. My passion really lies in creating a better world with technology, and I've been doing so for the last 10 years with my company SODAQ. So we are experts in low power, so using as little energy as possible to communicate data from the field, from devices, be it trackers or weather monitoring stations, to the cloud. We use energy harvesting, such as solar or kinetic or thermal energy to power the devices, and we try to make them, with the combination of those two elements, autonomous, so they run by themselves without an external power source, in an ideal case, forever. We were approached by a large player, buyer, Crop Science, to create a smart label, so a flexible label that can be put on every of their 180 million at the time parcels that they ship around the world with seeds. Also interesting for pharmaceuticals. And in here we have printed battery. We have, in this case, flexible etched PCB. And I'll show you a short video as to why we did this. Oh. Is there a way I can show this video? Sorry. Oh well, we will skip the video then, in that case. We'll share it, or you can find it actually on SODAQ's YouTube page, but basically showing different use cases of transporting goods around the world. These trackers can be used for monitoring temperature along the way, monitoring location, monitoring shock. So if the asset is knocked or handled poorly, knowing where in the supply chain that happens. And the real key component is that they communicate via cellular, so via the mobile network, which is was the world's first at the time we developed it for a printed solution. Now, one of the other reasons we did it in this way is that traditional asset trackers, which we've also been making, lead to a lot of waste in very hard to recycle batteries. And so with these kind of printed battery solutions, which is in this case zinc manganese oxide from a company called Imprint Energy, is fully recyclable, so can actually be fully taken back, and the components can be brought into a new production process, or can be separated with regular waste. Now, I'm going to talk a little bit about life cycle assessments, about environmental impact. There is, of course, a lot of factors to environmental impact. The one that I'll be pointing out a lot is actually the global warming aspect, so CO2 emission. The reason why I've selected CO2 emissions is because it's quite a known common standard that's measured across different industries, so we can make comparisons. But it's actually a very simplistic way to look at impact. I suggest looking at a company, Fairphone, and their impact reporting to really see state of the art when it comes to all the practices related to impact. In this case, we're also looking at environmental impact and the impact on people. So a traditional asset tracker like this one that we produced, in this case with a solar panel, I'll show you a use case in just a moment. It does about 17 kilos of CO2 equivalent emissions to make this device. So this is not for end of life, this is just to get it into this state and start using it. This compares to about 28 for a Fairphone, smartphone, and about 1.4 for a regular lamp. Comparing to some other things, 100 kilometers of flying is 125 CO2 equivalent kilograms, and a kilo of beef is about 100 kilos. So just to put that into perspective. And for example, a Mac Mini, 172 kilos. Now, that's just on the hardware side. And on the hardware, we also have an important component, which is the embedded software. This is what makes the device actually send as much data as physically possible from this device, so you get the most value out of it, because you're creating waste. Now you want to actually get value from this product. So what do? Well, we try to keep it asleep as much as possible. We try to work only when we really have to, so based on interrupts. So if there's a trigger like a temperature change or a sudden shock motion or a timer that goes off, and we communicate very briefly, and this is where actually the most power is consumed. So when we don't do anything, when we're sleeping, the device is always ready to wake up, but it only uses about 13 microamps or almost 14 microamps in that sleep state, which is almost nothing. When we work, we do around 1.3 milliamps, but this is only for 40 milliseconds to record an event. And then to communicate, we try to keep this as short as possible. This is consuming 176 milliamps. This is massive compared to its sleep state, but if you keep it short, then you can limit the total consumption of the power. We do it for 5 seconds to be able to transmit over the cellular network. For example, a Wi-Fi network scan can be in just milliseconds. A Bluetooth push of a message can also be just milliseconds, but cellular consumes quite a lot of power. Why cellular? Well, it's available globally, so if you want to track something from here to the other side of the world and not need infrastructure, then you will need to use cellular. Now, energy harvesting is great because that makes this product quite sustainable, because it can be produced once and it can be used for 5 to 10 years depending on the use case. And so if we use solar harvesting, we have sort of a respective reduction in negative environmental impact in terms of land destruction. I'll talk a little bit about use cases here. So the first use case is aviation logistics. Before we go into the label solutions, the last topic on this, we attach these to these air freight containers. Now these air freight containers, we can help to save 2 billion kilograms of CO2 equivalent emissions on just 60,000 of those containers for our client DHL. Knowing that to produce these, it's 17 kilos equivalent of CO2 emissions, then that means that we'll do about 1.02 million kilos of CO2 equivalent emissions to produce 60,000 of these. So that means we almost do 2 billion kilos of CO2 equivalent emission reduction by optimizing ULD, so unit load device route planning for DHL. This is a massive saving. However, we can still do better. And this is where I'm really interested to be here today, and how we're already starting to work with printed electronics, making them flexible, reducing the need for very toxic solutions like batteries, and changing the manufacturing process to go from etching, for example, to additive technologies. So in 3 steps, moving from FR4 PCBs to these kind of subtractive technologies to very interestingly, I'll mention them, but upcoming presentation is from Traxon. They do full additive manufacturing on roll-to-roll. Working with that technology will allow us to save even more for the environment. So to put it into perspective, between rigid and stretchable PCBs, you see that there's a massive reduction in raw materials needed, in manufacturing energy consumed, and also in the end-of-life disposal. Then, if we move from, let's say, flex PCBs to from subtractive to additive technologies, you see the significant reduction in materials needed on the right, very nicely visualized. And here you also see that energy consumption is significantly less. So in green is Traxon, our partner. They have significantly lower CO2 emissions as well, and material input and waste for additive technology compared to subtractive. Now, just to go back to the smart label. So we have this product. This product to make is 0.75 kilos of CO2 equivalent emissions. Here you see where it falls on the scale. So back to the image we had before. Significantly less. However, it also provides less of a lifetime. This will last about 3 months compared to the 5 to 10 years of this product. So why do we still do it? Well, smart labels can be embedded into boxes, can be made much smaller, and we can also make them in this form factor, adding a supercapacitor for energy and having wireless charging, and then they can be made circular. So moving actually from a, let's say, more wasteful one-time use product to a circular product. We can do full tracking of visibility along routes. So if you send a shipment of goods, monitoring where it is, what type of transportation, doing shock detection, temperature alerts. And I want to give one example. So we've also made a custom label for the pharmaceutical industry. So this is a typical medicine box. In here, we, next to the regular medicine and the booklets with information, we include this label. So this is kind of what the product looks like. That's inserted in there. There's a battery in there, also printed battery, and this is the current state of flexible electronics that's in there. The pharmaceutical industry has a loss of $35 billion every year just due to poor temperature control and logistics. Now, 2.5% of their annual revenue. This means 58.2 billion kilograms. In an ideal world, if we would send one label with each of these and reduce the temperature waste due to proper monitoring, we would be able to save up to 58 billion kilos of CO2 emissions. Now, this is a big number. Besides that, there's significant savings on financial terms for these pharmaceutical companies, being able to properly monitor their entire supply chain. Unfortunately, with a 0.75 kilos per label, we would generate an additional 140 billion CO2 equivalent emissions output for adding a label to every single box. That's a significant problem, and that's why I'm here today, because I'm not happy about this. And from a financial point of view, it's still going to happen. So that's a little bit of a problem. So a negative 81 billion emissions. And just like we are used to throwing our credit cards in the bin, that's also not good. So there are manufacturing or recycling techniques that are solving this problem, and we can make these products now fully recyclable in certain countries with certain recycling partners, but we need to keep innovating. So, for example, thinking of ways in which we can detach very easily the label from the packaging so that we can have it removed, so that we can bring components back into the recycling process and reuse components into the new manufacturing. Going to plant-based PCBs, I really like these, this innovation as well, fully soluble. And I was going to show you another video as well, but going into fully recycling the plastics that we use, so we can make full new enclosures based on simply shredding the plastics and then feeding it back into a molding machine. So kind of summarizing here, I've talked a bit about CO2 equivalent emissions. That's mainly in the design and manufacturing process. Ideally, we go from wasting resources, so using them one time and disposing of them, to reusing and recycling components. And that's what we're working on at the moment to improve. And in an ideal world, so that would be the grand vision, it would be to have a regenerative design. And I really like the presentation before with biodegradable materials. That's really where we want to go in the long term. So my name's Ollie Smeenk again. Please talk to me if you have any real-world applications that you're interested in working on. We still have a lot of problems that we're facing in actually becoming sustainable, and I'm happy to work with anyone on solving those. Thank you very much.
Thank you so much. So maybe we'll go with questions, if there's any. Well, I guess I will use a little bit the same question I had. So what about lifetimes? How do they work in different conditions, sensibility, packaging? I mean, it's tremendous challenge to package flexible electronics. How do you work, did you work on those challenges?
So we had a few different steps in there. So we've basically done like simple lamination, where you just have the battery riveted to the PCB, and then you laminate 2 layers of paper on top. It's a bit vulnerable this way. In here we actually use foam. So we laser cut foam on different layers so that there's more spacing where there's more spacing needed. For example, this area is where the PCB is, there's more space. But here it's thicker foam, and then cover it with a sticker. So that's really part of the production process. And in scaling, we have to do roll-to-roll, both for the PCB part as well as the full enclosure of the device.
And maybe what would you say was for you the biggest technological challenge in the development of your product?
Great question. I would say the biggest challenge in manufacturing this product was at some point the antenna design, so having something that works in all conditions. We've had situations where we've shipped a batch of labels to a warehouse somewhere, and the connectivity of the cellular network was not great there, so we've had to optimize antennas to perform better. Now it's actually the manufacturing at scale that we really struggle with. I think most mass manufacturers are kind of used to producing different types of solutions. You know, either less complex printed solutions or more complex entire devices. And that space in between, that's where there's a huge gap right now in the industry.
Thank you. Other questions from the audience? If not, let's thank our speaker again. Thank you so much.
Thank you, guys.